I'll actually be going over problem 2. Okay, 1 second.
Oh, wait, sorry. Victor's going to be going over problem 2.
Okay, so basically, what this problem has you do is there are n players, and each player takes 2 IQ tests, and then you're given the scores, the 2 scores that each player gets, and then you want to find the number of pairs of 2 players, such that one player scored higher than the other player on both IQ tests. So, for example, the pair of this second player with this third player
Oh,
is
Victor, I think you're muted.
No, Victor isn't muted.
Am I not?
I hear him fine.
We can hear him.
Okay. So anyway, so like for example, this the pair of pairs 2 and 3 is an established pair because 5 is greater than 4 and 3 is greater than 2. So the most immediate brute force solution that would come to mind is looping over all n squared pairs and then just comparing their scores to see if their pair is established. But that would take too long because n is 100,000 in this problem. So going through every pair would take n squared time, which would be 10 to the 10th in this case. And a good rule of thumb to like see if your solution will run on time is comparing the number of commutations your solution would have to do with 100 million. So which is about 10 to the 8th. So here 10 to the 10th is quite a bit larger than 10 to the 8th. So the n squared solution would for sure not run in time. So we basically need to find a faster way to do this, to count the number of established pairs. And to do this, I'm actually gonna visualize the input on like this grid. Okay, so we're gonna plot a point for every player on this 2-dimensional grid, where the first axis over here will represent the first score that the player got, and then this axis will represent the second score. So 5, 1 would be here. 4, 2 is here. 5, 3 is there. 1, 3 is here, and 2, 1 is at this point. So basically, here we can kind of like restate the problem. Kind of, we basically want to find the number of pairs of points such that one point is to the top left of the other point, because that would mean that, like, for example, this blue and the orange, if this blue is to the top left of the orange point, then that means that the blue's value is smaller in both axes, right? It has a smaller x coordinate, or like second test score, and it also has a smaller first test score. So we basically want to count the number of pairs that are in this arrangement, where 1 is to the top left. So here it seems like this still takes n squared time, because yeah, for every point you have to go over all the other points and then compare them. So as we try to come up with a faster way to count this, one idea that could work is basically looping over all the points, and then on the current point, being able to quickly figure out how many points are to the top left of it, right? Because that means that, like, this point would be to the bottom right of all the points to the top left of it, and then we would add that count to the sum. So for example, here, like, there's 0 points to the top left of this, so that would add plus 0. Same with the blue. The red also has 0 to the top left of it. The orange has a 1 point to the top left of it, which is the blue one. And then yellow has 2 points to the top left of it, which is the blue and the orange. That's plus 2. So this would give us a total of 3, which is the answer to the problem. So so if we can find a way to quickly figure out how many points are to the top left of a given point, then we would be able to quickly solve the problem. So then the question is, how do you do that, right? So you can use this technique called prefix sums. So to explain how prefix sums works, I'm actually first gonna illustrate it on a 1-dimensional array. So you can so then we can work our way up to a 2-dimensional one. So let's say we have this array A that just has some 5 values, and let's say there are n values total. In this case, n is 5, and then we want to create an array called pre, which will stand for prefix sums, which is the same length as the original array. So it has 5 elements again. And then each element in this prefix sum array will be the sum of a prefix of elements in the original array. So for example, this value here will be the sum of all these values here. Okay, so let's just write some values in pre to kind of illustrate this. So the first value would just be the first value in A, and then this value would be 2 plus 5, which is 7. This third value would be 2 plus 5 plus 1, which is 8, and then so on, right? So so here it seems like to compute this array of prefix sums would take n squared time, because for each of the n elements in the prefix sum array, we would have to loop over on average n over 2 elements in the original array and add them up. So then that's a total of n squared, like O of n squared time, which is slow. But what we can realize to make this faster is that there's actually a lot of wasteful computation going on. So say we're trying to compute what the value of this prefix sum is. So that's the sum of all of these 4 values. So to do that, we don't actually need to loop over all these 4 values and add them up, because we already performed the bulk of that computation in the previous computation of the previous prefix sum, right? This 8 already summed up the value of all the values we want except for just the current one, right? So basically what we can do to get this current sum is just adding this with this, and then that would give 10, right? So it would just add all the previous ones plus the current one to get the current prefix sum. And we can do the same thing to compute like the rest of the prefix sums. So this would be 13. And you can verify by like adding these numbers up. That would yield 13. So yeah, so now we see that computing a particular prefix sum only takes O of 1 time, just constant time, by just adding up 2 numbers. So then it would just take O of n time to compute this prefix sum array, where there were n original elements. So far, does anyone have questions over how this one-dimensional prefix sum works? I'm actually gonna code a code an example of this prefix sums just so you have like a more concrete understanding of it. So let's just use the original array, and then we want a array called pre. That would just be the same length, and then here, whenever you do something that like involves like building off of previous states, so like I would consider prefix sums like the most basic version of DP, even though like some people might think it's too basic. But like basically, DP just involve it's just computing the value of a current state based on the values of previously computed states. So here we always use the value of a previous thing, but then the question is like, there has to be some first value, right, that you use to build off the other ones. So like we would need some base case. So in this case, we know that the first value can just act as the base case, because the first value is just the same as the first value in the original array, and then all the other prefix sums can be built off of that. So we will just set pre of 0 to a of 0, just copy over the first element, and then we can loop over the other indices, and then just set the current prefix sum to the sum of the previous prefix sum and the current element. And then if we can print out this array just to show you that this does in fact correctly compute the prefix sum array for this given A. So right, so 2, 7, 8, 10, 13. That is what we expect. So that's a one-dimensional prefix sum. So next, we need to move on to a two-dimensional prefix sum, which will actually be used to solve this problem. So here I have just this array called matrix A of some random values here. And now in this two-dimensional prefix sum a matrix, we will define the value of a certain element. So like this element needs to be the sum of the elements in the rectangle, starting from the top left until this element. So like this value here should be the sum of all these elements, which is 17. So like this value should be 17 here. So let's say that, so let's just actually fill in a few values just so you you understand how this matrix is defined. So we'll just fill in a few values. Okay, so basically here let's just say we have these values computed, and then we want to be able to find the value of this value in the prefix sum matrix, right? So it seems like just like in the one-dimensional prefix sum, we would have to loop over a bunch of things to be able to compute this value. But we can actually try to do this more smartly by using previously computed states, just like in the one-dimensional prefix sum. But here it's a bit more complicated because it doesn't seem like there's an easy way to do this. But basically, we want to find the sum of the values outlined in red here, right? So let's try to use previously computed prefix sums to construct this rectangle. So let's say we try to do something like this. If we sum up this rectangle with like this rectangle, then that covers a lot of it. But the thing is that this inner section, this inner rectangle is being counted twice, right? Because there's an overlap between the yellow rectangle and the blue rectangle. So what we can do there is just subtract away this green rectangle, right? To only count everything in here once. And then of course we're still missing the value of here itself. So that we would just have to add that value itself. So here we can see that we can actually use the previously computed states to quickly compute the value of this prefix sum. So just to kind of continue this color coding, I will like label, so the value of this like in the first, in this thing. So so basically we're gonna have like a two-dimensional matrix we're gonna call grid. And the dimensions of this, we have to look at the constraint on S, which is 1000 here. So we're actually going to assign a variable for this, just so like our code is easier to read. So we're actually going to make this equal to 1001 because we want 1000 to be a valid index, right? Because the scores can go up to 1000, and then the dimensions of this grid will just be max S by max S. And then we need to proceed to read in the n pairs. So we're going to read in the coordinates of the current point and then increase it by 1. So the reason why we don't just set this to equals 1 is because like there could be multiple points on the same point, right? Like there could be multiple people who have the same scores. So we need to maintain like a count of that. So now at the end of this, grid will represent like this grid like we have here. And now we need to actually make the prefix sums on matrix, which will be the same dimensions as the original grid. And okay, one thing we need to think about when we're doing something like prefix sums is that we need to be iterating through the elements in order such that when we're trying to compute a current prefix sum, we've already computed the prefix sums that we need to compute the current prefix sum. So if we iterate through these cells, the cells of this matrix in like increasing a row and then increasing column. So like for example, like this formation, like this, then this will ensure that when we're on a given point, we've computed all these three because we know we've already traversed the previous row, which is these two, and then on the given row we've traversed the previous column. So we know if we go in like in this order, right, with increasing a row first and then increasing column, then that would like allow us to have the previously computed prefix sum values that we need. So here, the reason why, I'll explain why you go through like the constraints like this. So you start at 1 because we can start at 1 because the smallest score we can have is 1. So we can ignore the 0th column. And as you may remember in the one-dimensional prefix sum, we needed like this base case, right? We needed a base case to work off of in order to give all the future prefix sum states something to work off of. So here, this problem is pretty convenient for us because it basically provides us that like cushion. So here, since there can be no values in the 0th row or 0th column, we know that like let's actually make a new thing. So basically, we know that like all the values in the 0th row and column will have to be all 0 since like none of the coordinates can ever touch it. So like these will all be 0, and then we'd only start the thing. Like basically the grid would only pretty much actually be like this area. And this cushion is nice because imagine if you didn't have this these like zeros here, right? It was just this matrix. Then basically, say you're trying to compute like what is the prefix sum here, right? We want the sum of these values. So like you could be trying to access these elements, right? But they're out of bounds. So like that will like so we have to do some special case for those. In those cases, we would treat them as 0 because like the sum of the things out of bounds is obviously just 0. So like you would have to have like an if condition that checks like, oh, are we out of bounds? If it is, then treat this value as 0. But it works out here because if we have zeros padded along here already, then those values will be 0 for us already. So we don't need to like touch those. So that's why we can start with just ignoring the 0th row and 0th column and use those as like padded base case. And then we just use the basically the transition that we established here, right? The value of the current prefix sum is the value of the prefix sum ignoring the last column you're trying to add. I mean, the last row you're trying to add. So like here it's actually I'll code it like I wrote there. So like you first omit the first column. I mean like the last column, so the yellow, right? And then you add on omitting the last row, which is this blue, and then you need to subtract away the overlap, which omits the last column and the last row, and then you need to, of course, add on the current element itself, which is grid of ij. So at the end of this double for loop, we've computed the entire prefix sum matrix. So now we need to actually count the answer, right? So we're gonna store this in a long because, as we know, like n squared can be 10 to the 10th, which exceeds like the 2 times 10 to the 9th that int can store. So we're gonna have to now again just go through the entire matrix. We want to count. We basically want to add to the answer the number of pairs that have the current element as the bottom right. Like point. So we want to count how many things are in the top left of this point, right? So to do that, it has to be strictly to the top left of this, so it can't like share the same column or rows. So we're gonna have to add pre of oh wait, I actually just realized. Okay, I actually just changed the indexing I was doing. So let's change all of these to ij. We'll also change all of these to ij. Okay, so here we're gonna do I minus 1 times j minus 1, right? Because it has to be strictly to the top left, and then we're gonna multiply that by the number of points that are on a given cell. So that would be grid of ij. The reason why we multiply these is because like think about, so like say there's 6 points, like 6 people that have like this combination of scores, and then we have in this case there's 17 people that are to the top left of this. If you choose any one of these 6 people and you pair with any one of these 17 people, that would form a established pair. So yeah, that's how we can multiply these to count the number of to quickly count the number of established pairs, and then yeah, this will pretty much be our answer. So we can just print it. So you could actually do this, do these 2 loops together. Like you could just like copy and paste this code over like to here, but I just did them separately just so you could like understand the steps better. Okay, so let's submit this. Okay, so this solution works. So does anyone have any questions over the solution? Okay, I should just delete all my code, but there's actually some other stuff I want to point out here. So we have like a counting problem, right? So we want to count something. We need to make sure that we're not overcounting or undercounting the answer. So to convince ourselves that we're not overcounting, we know that we only consider a point as being the bottom right point in the pair, right? If we consider a point being the top left as well as the bottom right, then we would count every pair, every established pair twice, right? For example, in this one here, if you count the number of times it's a top left and when it's a bottom right, then you would count 1 for this blue, because it's the top left for this orange and also the yellow. And then when you're on the orange, you would also count, okay, I'm the bottom right of something. So then you would count this blue-orange pair twice. So the way we do it, by only considering when the current point is the bottom right point, we know that we only count points once. And then to convince ourselves that we do in fact count every point once, I mean like every established pair once, we know that we're traversing through every single point. So like we're considering every point being the bottom right point of some established pair. So we know that we're counting every established pair once and only once. So so like we can like be more sure that the solution is correct. Okay, so if no one has any more questions, I'll let Andrew present problem 3.